ஏப்ரல் 20 வியாழக்கிழமை இருக்குதா? அன்னைக்கு வைக்க மாட்டாங்க இன்னைக்கு. சண்டே தானே வைப்பாங்க. ஏப்ரல் 23 எலெக்ஷனா? நம்ம அன்னைக்குதான் இது பண்ணலாம்னு பார்த்தோம். அங்க உள்ளதான பட்டுசேலை கரெக்டா இருக்கா? உண்டு. ஆமாங்க. சாரிங்க. அம்மா அம்மா இந்த ஜார்ஜ் மேடம். பேர் அழகு எடுத்தா.
Hello everyone, welcome to the course Material Characterization by Professor S. Chankaran from IIT Madras. This is the live problem solving session for the week 8 of the course. I am Mayank Goyal. I am a research scholar in the Department of Electrical Engineering, IIT Bombay. The course is being taught by Professor S. Chankaran, who is an associate professor in the Department of Metallurgical and Materials Engineering, IIT Bombay. The course plan for week 8 is crystallized size, effect of strain on the intensity, profile fit, indexing, peak broadening in X-ray diffraction. So this live tutorial session is happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link. So first I will try to explain this week's topics. So here we are doing X-ray diffraction. So we are using X-ray interactions to characterize a material. So what will happen if an incident X-ray beam falls on a surface, on a material. So when an incident beam falls on a surface, so there will be absorption of the X-rays, and there will be scattering of the X-rays. So if there is absorption of X-rays, then the resultant would be either heat. So either the material will get heated, or it will release fluorescent X-rays, basically X-rays which are slightly larger in length, similarly to how we have fluorescence in visible light. Or it can also release electrons, which can be termed in three, which can be because of three phenomena. One is photoelectrons, where you where the X-ray energy brings a photon to the from the shell to the vacuum. So a photon, an electron from the shell to the vacuum, so electron gets released. That is called photoelectron. Or it can be an Auger electron, where the the electron inner shell vacancy attracts an electron from outer shell by absorption of X-ray. Or it can be Compton recoil. So in Compton recoil, you will have X-rays. So Compton in Compton recoil, so one electron will electron will bump into another electron, and that electron will get recoiled. So that there will be Compton recoil. Or there will be scattering of X-rays, which is generally of two ways: Compton method, which results in incoherent X-ray scattering. So where the X-rays fall onto the electrons, and the electron to electron interaction creates scattering. So that is an incoherent method. Or there is unmodified scattering, which comes from the lattice, which is coherent scattering. And this is the only way we can get structural diffraction information. So this is the only phenomena that is relevant to us here. So the coherent scattering originates at the electron. So an incident X-ray falls onto an electron, and so electron will be in an oscillatory motion. so that that oscillatory motion will create scattering in an as spherical wave fronts. So you can see an oscillating electric field gets converted into an spherical wavefront spherical wavefront EM wave. So the core concept is that the oscillating electric field of an incident X-ray forces an electron it encounters into an oscillatory motion, and that oscillatory motion causes accelerating and decelerating of electron, which emits its own EM wave, and this scattered beam will maintain the exact same wavelength and frequency as the incident beam. So it creates a strict and predictable phase relationship between the scattered beam and the incident beam, which we can then use for our diffraction analysis. So because an unpolarized X-ray beam has random electric field vectors in the YZ plane, we will average the component, and the Thomson equation will sum these scattered components to predict the exact intensity at any angle 2 theta. So that will be given by the formula I equals to I naught k by r square 1 plus cos square 2 theta by 2. So this 2 is the polarization factor because we are averaging over the YZ plane. So that's why 2 is coming. K is a constant that is encompassing the electron charge and mass, and r square is the decay defining the decay as we go farther from the electron. So the coherent scattering is called Thomson scattering, and incoherent scattering is called Compton effect. So coherent scattering occurs when entire tightly bound electron when the X-rays fall on the tightly bound electron cloud, whereas incoherent scattering occurs on loosely bound or free electrons. So coherent scattering creates elastic wave oscillation, an incoherent scattering is where the X-ray causes an electron to move. That electron that collides with another electron, and this way the energy is propagated, and those collisions result in loss of energy. Hence, there is energy loss which results in a wavelength shift, which is given by delta lambda equals to 0.0486 sine squared theta, whereas there is no change in wavelength in coherent scattering. And coherent scattering also maintains the phase relationships, whereas incoherent scattering will destroy any phase relationship. So now we are talking about scattering at the electron level, but now we talk at the atom level. So the nucleus is too heavy, so the Thomson equation will prove scattering intensity is inversely proportional to the square of particle mass. Since the nucleus is too massive to oscillate, all the scattering is done by the electrons. So does an atom with atomic number Z scatter a wave Z times stronger than a single electron? That would be yes, but only in the strict forward direction. That is, when all the electron waves remain perfectly in phase and their amplitudes act directly. So only when there is constructive interference, only that time the resultant resulting scattering wave will have Z times stronger intensity. So the paradox, when scattering at an angle, the waves are no longer traveling the exact same distance. So there it creates a path difference, and that path difference causes the waves to hit the wavefront slightly out of phase, and this partial interference destroys perfect addition, which will drastically reduce the net amplitude, and which will result in whether we are able to see a see some peak or not. And this interference creates a concept of atomic scattering factor, which is called F. So the atomic scattering factor F is the ratio of amplitude scattered by an atom compared to a single electron. And as the scattering angle increases, the individual electrons become increasingly out of phase. As a direct result, F decays rapidly. So atoms are highly inefficient scatterers at steep angles. So if the X-ray falls head on, then you will have the maximum intensity when theta is 0, and as theta increases, the atomic scattering factor will decrease. That is why if you see in an X-ray diffraction, as you go more and more theta, the intensity decreases. So so now first we talked in terms of single electron scattering, which is encompassed by Thomson equation. Then we talked about a single atom, which is encompassed by atomic scattering factor F. Now we'll talk about the unit cell, which is given by the structure factor, and this is what finally results in your X-ray diffraction peaks. So just as electrons inside an atom interfere with each other based on their geometric position, atoms inside a unit cell will also interfere with each other based on their fractional lattice coordinates. So the structure factor equation is given by summation of all individual atomic scattering factors. So to find the total lambda depth, we sum the individual scattering factors of every atom from 1 to n by mathematically shifting to their specific phase differences. So here we use the real lattice coordinates HUN plus KBN plus LWN. So this tells us the exact physical placement of the atom intersecting in the reflection planes. And this is added to the equation E part 2 pi iota, which which is the eh, component that calculates the phase shift caused by the physical position of the atom, and then Fn is the individual scattering factor, atomic scattering factor of an atom n, and then summing over all HKL values gives us FHKL. Summing over all atoms for a particular HKL value gives us FHKL. So this exponential function equals to n pi iota can be written as minus 1 power n, where n is an integer. So if n is even, then it will result in plus 1. If n is odd, it will result in minus 1. So plus 1 would mean constructive interference, that is, waves are perfectly in place. Minus 1 would mean destructive interference, which means waves are perfectly out of phase. So it acts as a mathematical toggle switch. So let's take the example of the primitive unit cell. So the origin of a primitive unit cell can be taken as 0, 0, 0. So if we put 0, 0, 0 in the equation, then h0 plus k0 plus l0 will become 0. So it will become e power 0, which is 1. So the resultant capital F will be equal to small f. So for a unit cell containing only one atom at the original coordinates, the entire phase collapses mathematically to 1, and the resulting intensity F square will be equals to the intensity small f square. So the scattering intensity is completely independent of reflection planes. So every possible plane in this simple crystal will reflect X-rays. So we will be getting X-rays from every possible plane, and their intensity will be then defined by other factors such as theta, as we studied now. So, so why did we take just this point and not any other point? So, when we are calculating for the structure factor, we only take the origin of a lattice which forms a cube. So this is because in a cube, you take any point, any vertex on a cube, it will give the same result. So hence we don't consider we only take the origin of a cube. Now, if there are if there are atoms that do not fall on the vertex of the cube, we then we consider that as a second sublattice, and we take the origin for that sublattice. So for a simple cubic case, we only take the atom at 0, 0, 0, and we find that it will reflect for all possible planes, all possible HKL values. Now we take the case of a base-centered lattice, where you have atom at the bases, bottom base and the top base. So here you will see that if we take just this point, then the cube that is formed will not consider this point. So we take this whole lattice as a sum of two sublattices, one with this as origin and one with this as origin. And then we calculate for this. So the coordinate for this is 0, 0, 0. And if you find the coordinate for this, it will come as half, half, and 0. And then we sum individually for these two. So for 0, 0, 0, this whole thing becomes 0. And for half of 0, it will become h by 2 plus k by 2 plus 0. And then this 2 will come inside and subtract. So this then mathematics simplifies to f equals to small f 1 plus e per pi iota h by k. So by adding a second atom at the phase center, the waves are scattered by the waves scattered by origin atoms must interact with the waves scattered by the center atom. So now the result hinges entirely on whether the sum of h plus k planes yields an even or odd integer. So for a base center lattice, if this h plus k will be even, then this will become 1. So this will be 1 plus 1, 2f. So we will have a reflection. If h plus k is a negative and is an odd integer, this will become minus 1. So it will be 1 minus 1, 0. So your structure factor then becomes 0. So a structure factor becomes 0. That means we won't see any peak for that plane. So you can see here, if h and k are unmixed, that means both are even or both are odd, then their sum will be even. So the structure factor will become 2f and the intensity will become 4f square. If they are mixed, that is one is even and one is odd, then the sum will be odd integer and the structure factor will be 0 and the intensity is also 0. So you can see, if since HKL are only integer values, so h plus k can only be an integer. So intensity can only be either 4f square or absolute 0. So you can see, by adding a second atom at the base positions, we are also able to annihilate specific X-ray reflections. So you can see, if we have 111, 112, 113, 021, 022, 023. So the L value here is irrelevant. Only H and K are relevant. So they are unmixed. Here and H and K are unmixed. So you will have very high diffraction peaks. And when H and K are mixed, they will be completely absent, systematically absent from the diffraction spectrum. So you see, by tracing the journey of a photon from a single electron collision up to through the geometry of a unit cell, we are able to get absolute precision of crystallography, and the spatial arrangement of atoms systematically writes the rules of interference, allowing us to read a crystal structure by looking at the light it refuses to reflect. So the light it is not reflecting, and the light it is reflecting. By that we are able to figure out what is the structure of the atom, of the lattice. So now we talk about, let's say, bodies BCC crystal, that is body center crystal. So in a BCC crystal, the X-ray diffraction yields a strong peak in for 200 planes, but for 100 the peak for 100 plane is entirely absent. But we from last week we know that 200 plane is nothing but a sub sub plane between 100 planes. So why does it give for 200 and not 100? So what happens is that, so there is the first ray that is coming here and going from here, and the second ray can either fall in the C on the C plane, which is your 100 plane, or on the B plane, which is your which is your 1200 plane. And when that reflects, so when it reflects, so the wave from the 200 plane will completely cancel the wave from the 100 plane, because they will be entirely out of phase. So hence the 100 plane will have the peak for 100 planes will not have any intensity, because they will create destructive interference. So for BC, if you calculate for BCC, so if you see here for BCC, so your the the so it again, the cube formed by this origin atom does not contain this atom. So we take a second sublattice with this as origin, and the position for this would be half of half. So if we add that to the, so the final structure factor you will get is this: f h k equals to f summation e power iota pi h plus k plus l. So you can see, if you have even h plus k plus l, then there will be constructive interference, and if you have odd h plus k plus l, so this again would have a 1 plus factor with here, which is not shown here, but this will be e power iota pi h plus k plus l plus 1. So if h plus k plus l is odd, this becomes minus 1. So minus 1 plus 1 becomes 0. So FHKL becomes 0. So for odd states, it will be destructive interference, and you won't see any peak. So the structure factor translates the CD atomic coordinates of a unit cell into a simple binary state. So either constructive or destructive interference. So for body centered cubic, the formula would be FH plus HKL equals to F 1 plus iota E pi H plus K plus L. So if H plus K plus L is even, these are allowed peaks where HKL becomes 2F. If H plus K plus L is odd, so these are forbidden peaks where FHKL is 0. Now if we come to face centered cubic, so there you will have a lattice here, lattice point here, and a lattice point here, and a lattice point here. So it will have 3 lattice points, actually 4 lattice points, I think. And if you sum it up, so you will get like this. So for all the 4 lattice points, you will have formulas like this. And if you see here, so if H plus HKL are all even or all odd, then you will see this will all this will all sum together, and FHKL will become 4F. So these will be allowed peaks. And if there is any mismatch in HKL, then this whole thing will become 0. So this will result in forbidden peak. So you see these are called HKL selection rules, and they are different. So depending on the lattice structure, they will be different. For simple cubic, for base centered cubic, for body centered cubic, face centered cubic, for all of them, the HKL selection rules are different. And by seeing which peaks are present and which peaks are absent, we are able to determine whether it is simple cubic or face centered cubic or body centered cubic. So for body centered cubic, the allowed reflection rule is that H plus K plus L should be even. For face centered cubic, the allowed reflection rule is that HKL must be unmixed. That means all of them should be even or all of them should be odd. So now, so till now we were considering that our our lattice contains only one atom, only one type of atom. Now we will consider lattice where which contains two atoms. Let's say cesium chloride. So it contains two atoms CS and Cl. So now the structure, atomic structure factor F, that will be different for both atoms. For cesium, the F would be different. For Cl, the F would be different. So we can't just cancel out the F's for each of them. So in cesium chloride, the what happens is that one atom is on the edges and the other atom is on the body center. But this is not a true BCC lattice because the structure factor for both of them are different. So what will happen if H plus K plus L is even? Then we will have the sum of peaks. So FCl plus FCS. So which will give us high intensity. And if HK plus K plus L is odd, so earlier it would have been F minus F equals to 0. But now the F's for both are different. So now we'll have the difference FCl minus FCS. So we won't have zero intensity, but we'll have low intensity. So there will be some order of disruptive interference, but not completely out of phase, not complete interference, complete destruction. So we will still get peaks for both of them, just the intensity would be different. Now in case of sodium chloride NaCl, so both both the sodium and chloride both individually form FCC lattices, and they are displaced in some amount within each lattices. So so if you if you calculate the if you calculate the structure factor of this, you will find out that if HKL are all even, then there will be sum of the peaks, that is 4 times FCl plus FNA. If they are all odd, then there will be difference peak, that is 4 of FCl minus FNA, that will be reduced intensity. And if HKL are mixed, that means mixture of odd and even, then that will result in a forbidden peak, because both individually Na lattice and Cl lattice will cancel out the intensities. You see, if in a single atom system, so the intensity scattering intensities are the same, So if they are out of phase, they will completely cancel each other, and the resulting will be zero peak. In a two atom system, stru- the scattered intensity will be different. So even if they try to cancel out each other, there will be some remainder left, which will result in some amount of peak intensity. So, so the structure factor doesn't just predict where a peak will be; it also proves exactly what atoms are sitting in the lattice based on how effectively they cancel each other out. So by seeing how much they are adding up and how much they are subtracting, we can also figure out which are the atoms present in the lattice. Now we come to anatomy of an X-ray peak. So an so the structural factor that we were studying before, that just determines the intensity, that just determines whether there is a peak or there is not a peak. But there are six distinct physical phenomena that dictate the final integrated intensity of the peak and the shape of the peak. So so there is first amplitude of the peak or the peak height, which is given, which comes from the structure factor and the polarization factor. Then there is peak width or base, which which comes from Lorentz factor and temperature factor. Then there is integrated area under the peak, which comes from the multiplicity factor and absorption factor. So this is a true measure of intensity, and not just the peak intensity is the true measure. So if you want to measure the intensity of an X-ray peak, you should be considering the area under the peak and not just the peak intensity at this point, peak amplitude intensity. So there are different hardware experimental hardwares to measure X-ray diffraction. One is Lau method, in which the angle is fixed and the wavelength is varied. Then there is rotating crystal, in which the wavelength is fixed and the angle is variable in part. And in the powder method, the wavelength is fixed and the angle is varied. So to measure the missing and difference peaks calculated by structure factor, the experimental methods must strategically lock either the wavelength or the physical angle to satisfy Bragg's symmetry. You cannot vary both of them simultaneously. You have to fix one of them and vary the other. So the ideal peak is like a straight a straight bump in the intensity at the diffraction angle. So that should be what ideal peak should be. But the reality is that we have a peak like this, a broadened peak, which has a maximum intensity Imax, a full width half maximum. So a full width at half maximum means basically, say you take half of Imax. So if Imax is at 50, you go to 25 and you take the full width at 25, which comes from an angle 2 theta 1 to an angle 2 theta 2. So that is called your FWHM, or full width at half maximum. And then third is your integrated intensity, that is area under the peak. under the curve. So the core goal of XRD analysis is to understand why mathematical equations predict the perfect sharp line on the right, but laboratory reality produces a broadened curve on the left. So, so by converting this, by by bringing in factors to that broadens this peak, we can understand the exact phenomena that is giving us these peaks. So the ideal intensity should come from I equals to f square p 1 plus cos square theta divided by sin square cos theta into a theta e power minus 2m. So your p is your multiplicity factor, which is the relative portion of h scale planes contributing to the same reflection. So in a cubic system, 111 and 100 will have different number of geometric variants. So they will have different multiplicity factor. The the central formula is your Lorentz polarization factor. So it gives the geometrical angular distribution of the sample. So it accounts for the fraction of crystals that in the orientation that satisfy diffraction within a given tolerance. So in an angle, a particular number of atoms will be present which will satisfy. So that is given by this Lorentz polarization factor. Then there is your absorption factor. So it is a material property that defines the physical absorption of X-rays as EM radiation interacts with the matter. So that will also depend on your angle. So because as you change the angle, the number of atoms interacting with the X-rays will also change. So it's given as A of theta. Then there will be a temperature factor E per minus 2m. So it accounts for atomic thermal vibrations, which increase the interatomic plane distance. It depends on vibration amplitude and scattering angle 2 theta. And then F you already know is your structure factor. So the Lorentz factor and angular tolerance. So it gives, so diffraction does not instantaneously drop to zero the millisecond a crystal rotates away from the exact Bragg angle. There is a there are planes oriented slightly away from theta b by a margin of delta theta, which will still geometrically contribute to scatter photons to a reactor. So it's not like it's not like if my peak should come at 10 degrees, so at 9.9 degrees I will have zero intensity, and at 10 degrees I will have very high intensity, and then again at 10.1 degree I will have zero intensity. There is a tolerance cone, some tolerance margin delta theta, which will also contribute to the peak, to the scattering. So so the exact Bragg angle is perfectly synchronized with the ideal mathematical lattice. Tolerated angle is slightly misaligned, but it is within the geometric survival threshold. So there are still, so it is there is misaligned, but there are still scattering happening at this point. So at Bragg angle there will be complete conceptual interference, whereas at tolerated angle there will be partial interference. So there will be some part that is cancelled out and some part that is present. So the intensity would be less, but it won't be zero. So what happens is that at the Bragg angle, Bragg angle defines a peak, absolute peak maximum. So the Imax will occur at Bragg angle, and at tolerated angles, you will have tails or the broadened base of the integrated intensity curve. So the the tail that you see coming from the Imax on both sides, that is due to your tolerated angle. So the broadness of an X-ray peak is entirely composed of these off-angle rays surviving the journey to the detector. So at the exact Bragg condition, the crests align perfectly, and this amplifies the wave, which generates a massive signal at the detector. But at any off angle, if if the say if it does not create complete disruptive interference, we will still have rays that are going to the detector. So so a fraction of waves will not cause complete disruptive interference, and therefore the immediate surface layers cannot cancel out off angle mistakes. So there will be still some amount of scattering amplitude. So the total cumulative error is exactly half of lambda, that is out of phase. So the burden of destructive interference falls to the deep layers, because deep layers are scattering at a higher angle, are creating a larger path difference, which will help us creating a more intense destruction. So to completely phase out a single off angle surface ray, there must exist an m+1 plate deep inside the crystal that is exactly half a wavelength out of phase with the surface. So if we want to cancel out the surface ray, we need to have a deep plane that will cancel out this ray. So what happens is, in a bulk crystal there is very large depth. So we have those deep planes that exist for cancellation. So that is why the off angle rays will be cancelled out. So we will just have very sharp, very neat X-ray peak. But if we take a very thin film, like a nanoscale material, which has a very thin. So due to that, due to it's very thin, it does not have those deep planes to cancel out the surface rays, and due to which the it is not able to cancel out a lot of peaks. And what we result is broadened and messy X-ray peaks, as you can see here in this. So you can see by looking at, so the broadening is also dependent on the size of your crystals. So destructive off angle surface rays need destructive interference, a depth for destructive interference. So if when a crystallite is refined to the nanoscale, it physically lacks the deep atomic planes needed to cancel out the off angle delta theta rays. So those errors survive and result in broadened peaks. So in bulk crystal, the deep planes are abundant. You have more than you have multiple deeper layers available. But in nanocrystal, the grain boundaries truncate the availability of deep planes. So in bulk crystal, it results in complete of complete phasing out of complete perfect phasing out of off angle rays by deep lattices, and results in sharp narrow diffraction line. But in nanoscale crystallite, the deep planes do not exist, so off angles survive and hit the detector and result in broadened diffraction curve. So the broadening is not a machine error, It gives the exact physical signature of missing atomic depth, which is coming from your crystallite size. So how do you mathematically determine this excess broadening? So for that we consider the full wave at half maximum. So as you increase the number of planes m, so as you decrease the number of planes m, the angular range from 2 theta 1 to 2 theta 2 will increase. So the width of the diffraction, so from this we can understand that the width of the diffraction curve scales inversely with crystal thickness. So at full wave, if we consider full wave at half maximum, so we so it's it's given as half of 2 theta 1 minus 2 theta 2, so it gives theta 1 minus theta 2. So it tells us the full angular width where the off angle diffractive intensity finally drops to 0. So so by so in XRD, the exact location of the peak, that is the theta value, gives us the crystal structure and atomic spacing, and the broadening of the peak or the full width half maximum gives us the gives us the precise ruler for measuring the grain size in nanoscale. So in modern material science, XRD is not just merely a tool for finding the perfect lattice. By measuring the surviving off-angle photons, we can directly calculate the physical boundary of our nanomaterials. So we can calculate how the size of our nanomaterials. So in a perfect lattice, at the Bragg angle, the rays scatter exactly in phase, and they constructively interfere, which is given as lambda equals to 2d sine theta, and the result is a theoretical infinitely sharp diffraction peak. But in reality, at an angle, as we go away from the Bragg angle, there are some surface rays which still result in partial interference and give a signal. So it creates a curve instead of a line. And if we have an infinite crystal, a deep plane will completely cancel out this off angle theta ray, and we'll have a sharp we'll have a sharp peak. But in nanocrystal, these deep planes don't exist. So the diagnostic rule will be that as the crystal thickness decreases, the angular range of uncancelled rays increases. That means smaller crystal lead to broader peaks. And if and when we derive, so now we can derive this effect. So we can calculate the limiting angle for zero intensity. So so if we go for a higher angle, so 2d sine theta 1 will get cancelled for m plus 1 lambda, and lower angle 2d sine theta 2 will be cancelled out at m minus 1 lambda. Now if we subtract and apply trigonometric identity, so we'll get 2t cos theta 1 plus theta 2 by 2 sine theta 1 minus theta 2 by 2 equals to lambda. And if we take the limiting case of assuming theta 1 and theta 2 equals to theta b, we get that T equals to lambda by B cos theta, where T is your thickness of the material or the grain. So the thickness of crystallite or your grain. So this is called Scherrer's formula. So T equals to 0.9 lambda by B cos theta B. So 0.9 is your shape factor, which is instead of 1 it's 0.9, so it's more exact treatment. Lambda is your X-ray wavelength, T is your crystallized thickness size, theta B is your Bragg angle, and B is your angular width, that is full width at half maximum, FWHM in so it's in radians, not in degrees. So you can see so if you have a 1 millimeter crystal diameter for lambda equals to 1.5 angstrom, D equals to 1 angstrom, and theta equals to 49 degree, your broadening V will come out around 2 into 10 per minus 7 radians, which is like imperceptible, you cannot measure it. But if you have a 500 angstrom thick crystal, so since D is your 1 angstrom, so it contains like 500 planes, since the thickness is 500 angstrom. And now if you calculate B for the same values of lambda, D and theta, you will get 4 into 10 per minus 3 radians, which is easily measured by an X-ray detector. So peak broadening due to size is exclusively a nanoscale diagnostic tool. So if you have very small crystals in nanoscale, then only you can use this peak broadening method to calculate size. For very large crystal diameters, the broadening due to size is very small. There will be still broadening, but they will be due to other factors, not due to size. The measurable broadening, I mean. The measurable broadening will not be due to size. They might be due to other factors like the instrument. So if you try to apply those on the if you try to apply that broadening to calculate your size, you will get a wrong value, because that broadening is not coming from your size. Your broadening coming from size is very very small and not detected by the detector. So only when you are measuring very small particles in nanoscale, then only you can use the peak width to measure your size. So next would be lattice strain. So real materials are polycrystal networks of interconnected grains. So they are not just one single lattice. There are multiple lattices arranged at different grain orientations. And when forces are applied, adjacent grains, let's say one at theta b and the neighbor at theta 1, they will experience stress differently, and that will alter the diffracted signal. So one peak will shift to the left, other peak will shift to the right, next peak will again shift to the left. So we must be able to distinguish between the two scales of stress to decode the XRD pattern. So there can be micro stress, which is uniform over large macroscopic distances. The effect would be that entire lattice will be either uniformly stretched or either uniformly compressed. So the XRD signature would be the entire diffraction, all the diffraction lines will shift in micro stress. So it varies grain to grain or within a single grain. So, so the effect of lattice would be that within the same area there will be a distributed range of D spacings. That is, for the single orientation there will be multiple D spacings, and that will cause your interference at different wave angles. So it will result in a broadening of your diffraction line. So in one case your diffraction peak will shift itself, in another case it will broaden. So if you take case 1 where there is no strain, so you have this diffraction line. In case 2 you have a uniform strain in your lattice, which so that will result in your a shift of your diffraction peak. Then in third case you have non-uniform strain. So in one case you have a distance, your lattice plane distance is less than d naught. In other case the plane distance is greater than d naught. that results in diffraction at different points, and it will cause broadening of the peak at the same diffraction point. Or there can be a shift also in the peak in the peak in the peak intensity depending on your strain. So deriving the strain differential, Bragg's law gives lambda equals to 2d sine theta. So if we differentiate it with respect to theta and d, we get delta 2 theta equals to minus 2 del d by d tan theta. So your del d by d, it represents the non-uniformity in strain, and this delta 2 theta gives you the angular broadening beyond the instrumental error. So the broadening is directly proportional to your variation in lattice spacing. So if you see, if you apply the size constraint, your peak broadening is proportional to 1 by cos theta. If you take your deformation constraint, then the peak broadening is proportional to tan theta. So both of them will result in different peak broadenings, different type of peak broadenings. So the total observed peak broadening will be a compound signal of instrumental error, limited crystallized size, and non-uniform lattice strain. And differentiating them is the key to characterize your material. So that is the topics for today. Now I will give you some practice questions to help you understand this better. Question 1: which of the following statements is correct in the case of X-ray diffraction? The intensity of different diffracted wave increases in the angle of scattering as the angle of scattering increases. The elastic scattering of X-ray photons by an electron is called Compton scattering. The polarization factor is because the incident beam is unpolarized. The penetration depth of a laboratory X-rays is in the range of few millimeters. You can write in the chat your answers. So the answer to C, this is C. The polarization factor is because the incident beam is unpolarized. So since it is unpolarized, so at different at different angles there will be differences created by the beam. So so we have seen that as the angle of scattering increases, the intensity of diffracted wave decreases. So this is the incorrect option. The elastic scattering of X-ray photons by an atom is called Compton scattering, which is wrong. It is Thomson scattering. Compton scattering is inelastic and incoherent. The penetration depth of a laboratory X-rays is in the range of few millimeters, which is wrong. It is in the range of few microns. So now let's say if you have a material, if you are if you have a very thin material which you are depositing on another or on a substrate. So let's say you have a powder material and you put it on glass slide and that you keep in your X-ray. Now the thickness of your material, your powder material or a liquid or a dried material will be in, let's say, maybe 1 or 2 microns at max. Or if you want to go very thick, it will be like 10 microns, which is much less than the penetration depth of X-rays. So your X-rays will also go deeper in your glass slide. And so can anyone tell what so if from what is the X-ray spectrum I expect from a glass slide? So a glass is an amorphous material. It does not have a proper lattice. So it will not create. It will not have any. It will not give any of your Bragg peaks. So it will only give a. It will only give continuous spectrum. So you will have a. So you will have a background spectrum in your X-ray diffraction spectrum. And let's say instead of glass slide, you use a crystalline material like silicon wafer. So now, when your X-rays will go deeper in your silicon, they will experience another lattice. So from that lattice, they will also give out peaks. So the resultant will have your peaks from your material as well as your silicon substrate. So you will have to figure out which are the peaks from a material and which are the peaks coming from your substrate. Suppose we have characterized a crystalline material through XRD, which has gone through two types of treatments. One is fully annealed and another is heavily cold work. What will the effect on X-ray peak broadening? Annealed material will show higher peak broadening as compared to cold work material. Cold work material will show higher peak broadening as compared to annealed material. As long as we are characterizing the same material, there is no effect of on peak broadening. Both the conditions will result in higher peak broadening. So the answer will be cold work material will show higher peak broadening as compared to annealed material. So what happens is that if you take a crystalline material, so any it won't. It's not like it will be completely single crystal. It will have some grains. So and as we know, so each grain, the size of the grain will give us the peak. Size of grain will give us the peak broadening. So when we anneal a sample, what happens is that the grain size will increase. So we'll have larger grains, and the larger grains will result in smaller peak broadening. But if you have a cold work sample, then you are not increasing your grain size. So that will have a higher peak broadening. So the correct answer here is that cold work material will have show higher peak broadening compared to annealed material. Suppose an X-ray beam is scattered from a cubic crystal. Which of the following sets of planes will be having the highest intensity in the forward direction? 111, 200, 220 does not depend on the type of planes. So the answer is A. So we studied the formula for calculating intensity. So if we just considering the set of planes, so we'll have to look at which has the highest multiplicity factor. And here 111 out of these three options, 111 will have the highest multiplicity factor, so it will result in the highest intensity. Which of the following sequence of peaks will appear for a disordered FCC material? 111, 200, 220, 311, 110, 200, 211, 222, 100, 110, 111, 200, 110, 111, 200, 211. So the answer is A. So we studied that for an FCC lattice, only the HKL must be either all even or all odd. So we see in the option B there is 110, which is mixed of even and odd. C, D, all of them have values which are mixture of even and odd, so they are invalid. In A, 111 is all odd, 200 is all even, 220 is all even, 311 is all even. So only this is the correct answer. Which of the following conditions is true for X-ray reflections of NaCl according to the structure factor rules? Peak intensities are lower for HKL having all even indices. Peak intensities are higher for HKL having all odd indices. Peak intensities are higher for HKL having mixed indices. Peak intensities are zero for HKL having mixed indices. So the correct answer would be D. so so for so we studied that for NaCl, F equals to 4 FNA plus FCl when HKL are all even. F equals to 4 FNA minus FCl when HKL are all odd. And F equals to 0 when HKL are mixed. So out of all four of these, only D satisfy these conditions. So D is the correct answer. Compressive strain in the material will result the XRD peaks to shift at lower angles, to shift at higher angles, to increase the intensity, to decrease the intensity. So the correct answer is B. So when you apply compressive strain to a material, so it will its lattice planes will come closer. So the lattice spacing will decrease. Your D value will decrease. So if D value decreases, your sine theta value should increase. That means your theta value should increase. So it will shift the peak to a higher angle. So B is correct. The structure factor of a crystalline material having atoms sitting at coordinates 0, 0, 0 is F, 2F, 3F, 4F, where F is the atomic scattering factor. So the correct answer would be A, F. So this we studied. So 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 for atom at 0, 0, 0, the it will be H0 plus K0 plus L0. So which will become e power 0, which will is 1. So this F, capital F will be equal to small f. So A is the correct answer. Given lambda equals to 1.5 angstrom, FWHM equals to 2 into minus 7 radian, and Bragg angle at 60 degrees, what is the average crystalline size of the material? 135 nanometer, 300 nanometer, 40 nanometer, 450 nanometer. The correct answer would be T equals to 135, but so it won't be 135 nanometer actually. So it will be zero point 0.9. So point cos 60 would be half. So 2 into minus 7 into half will be 10 per minus 7, which will come into numerator as 10 per 7. Zero point 0.9 into 1.5 would be 1.35. So it will be 1.35 into 10 per 7 angstroms, which comes out to be 1.35 millimeters actually. So the correct answer should actually be T equals to 1.35 millimeters by this these values. So those are all the questions I had for today. If you have some doubt, you can ask, or if you want, you can leave the chat.